Hi, my name is Alex, and this is Watch Repair Tutorials. If you're new to the channel, I'm a retired watchmaker, and I make videos for people who are excited about learning watch repair. This is lesson 8 of our series on getting started in watchmaking. Now that our movement is back together and lubricated, we're going to cover the basic principles of regulation. I'm also going to answer a couple of issues that some of you are having over oiling the end stones, questions about how effective the technique I showed you for lubricating the pallet stones is, magnetism, and what's causing the low amplitude some of you are having after your first service. Okay, let's start with the low amplitude. If you're having issues with low amplitude and you are using the ST3600, you are using the recommended oils, and you are not damaging anything. The issue is your oiling technique. We know that the pivots are good. We have a new mainspring in the movement. We don't have any wear in the powertrain. The escapement is set up correctly, and the balance wheel and hairspring are okay. And when we tested the movement before we even started, we had good amplitude, right? So that pretty much leaves the lubrication. This is exactly why you start the learning process by working on a new movement. It gives you the opportunity to work out and understand how to lubricate the powertrain and the escapement, as well as getting the confidence that what you're doing is correct. If you just pick up some random vintage watch and you service it, and then you come up with low amplitude, how are you going to know that it's not your lubrication that's causing the problem? Well, you don't. You end up chasing your tail all over the place looking for all these other issues when the problem is just inadequate lubrication. So that brings us to the next question that I've been getting a lot of. How do I prevent the over-lubrication of the end stones? Well, there's a whole science revolving around how to pick up oil from the oil pot. And I did a video about it a couple years ago, so I'll just leave a link into the show notes if you're interested in learning about that. Properly oiling the end stones is critical for how well your movement runs and whether you'll be able to regulate the rate to an acceptable level. The goal is for the spot of oil to be centered on the end stone and cover about 50% of the end stone surface. That way, when the end stone is laid into the shock setting with the balance jewel, the oil is slightly compressed like the cream in an Oreo cookie. If it's too much, then the oil gets pressed out over the edges of the end stone, and then it travels around the edge of the stone, pulling all the oil out of the setting. To solve the problem with picking up too much oil, I'm going to reshape the tip of the oiler. Here I'm using what's known as an escapement buffing file to reshape the tip, but you can also do the same thing with a high grit sandpaper like 1500 or even 2000 grit. You just slowly drag the tip across it to reshape it. And after I get the tip down to where I like it, I'm going to give it a bath in Epilam. The type I'm using is called EpiSurf. Now, after a short drying period, it's back to the buffing files to remove the Epilam from the tip of the oiler. Now, when I dip into the 9010, my oiler only retains a small amount on the very tip of the oiler that doesn't have the Epilam. Now, when you transfer the oil to the end stone, you're only depositing a very small amount. If you need more, then it's easy to just add another tiny little drop. If you don't want to go through the modification process like this, then your best bet is to watch that other video I made and just work on your dipping technique. Next, the people asked about the method of oiling every third tooth of the escape wheel and whether that was the correct way to do it. I think this is primarily asked because they've seen or read that the 9415 should be added to the actual impulse face of the pallet stone. Now, while that may be a more exact way to deposit the grease, very few new watchmakers are going to be able to do that. It takes very high magnification and a very steady hand to be able to make that deposit while the pallet fork is installed in the movement. This is something that most of you might not be able to do at this point. Heck, this is your first watch service. Now, I demonstrated that technique a year or so ago in my first beginner series, but I really think this method that I'm showing you now is more suited to more people at this level right now. To know for sure if the correct amount of grease has been deposited, you have to be able to see that space between the impulse surface of the jewel and the impulse face of the escape wheel. And you have to look to see how much oil is present in that little angle. Tough to do without a lot of magnification. Here, you can see that we have a nice stripe of 9415 right down the middle of the jewel. It may not be perfect, it may not be to Omega specs, but as a new watchmaker, this is a huge improvement over just slathering those jewels with too much oil. Now, another issue that's reared its ugly head is magnetism. So I wanted to talk briefly about this as well. Demagnetizing should be part of everyone's service procedure. It's good to do it before you take your initial readings, after the parts are cleaned, and even before regulation. The problem with the force of magnetism is that you can't really see it. Now, you can see the effect of it when you see a screw stick to your tweezers or your screwdriver, but many people are fooled into assuming there is magnetism present when there is really not enough magnetism to affect how the watch is going to run. Now, what do I mean by that? Well, you have to understand that all ferrous metals, including steel, can have some level of magnetism present. Not enough to affect the parts in a watch negatively, but enough to be detected by a compass, which is what a lot of people use to determine if something is magnetized. This, coupled with the fact that all demagnetizers are not created equal, causes many people to see that needle on the compass move, think there's a problem with magnetism, and then they try using one of those little blue $10 demagnetizers and actually end up magnetizing the very thing they were trying to correct. The developer of an app called Magnetized Wristwatch Checker reached out to me last year to show me how his new app works, and it really blew me away. And we had extensive conversations, and it really opened up my eyes a lot to the science behind magnetism and how it's measured. So, looking at the app, once you've got it downloaded, the first thing you have to do is you have to calibrate the sensor. Now, the calibration takes into account any background electromagnetic field, which, includes Earth's magnetic field and other ambient sources of magnetism that might be around you. This ensures that the app provides accurate measurements of the magnetism specifically related to the object that you're testing. The directions are all clearly outlined in the app, but basically what it's saying is that once you've got the calibration done, don't move your phone. You have to calibrate the sensor anytime you move it or open the app. Now, once calibrated, you need to find the sensor that's in your phone, and this is called the magnetometer sensor. And they are very sensitive. Sensitive enough to detect very weak magnetic fields, like the Earth's magnetic field. Its sensitivity is what really allows your smartphone to work like a compass. You find the sensor by slowly moving a piece of steel a half inch over the screen until you get your strongest sensor on the meter. The sensor will be below that point. Now, these three lines, the red, the green, and the yellow, they represent the three directions it's measuring magnetic fields in. It's measuring left to right, forward and reverse, and magnetic fields that are going up and down. So now that you've calibrated the app and you know where the sensor is, let me show you how this works. Now I'm going to take a screwdriver that's not magnetized and I'm going to hold it over the sensor. You can see that it is showing a small amount on the sensor, but when I test if a tiny screw is attracted to it, you can clearly see that it's not. Now I'm going to magnetize the screwdriver with a floor magnet. Visually, you can see that the screw now is attracted to the screwdriver. And when I hold it over the sensor, you can clearly see the difference in the reading. Now I'm going to demagnetize it with my Elma demagnetizer. Check it to see if the screw gets picked up, which it doesn't. And look at it on the app, and you will see now that it's back to its normal level. So this screwdriver is clearly now demagnetized. I've had tons of questions about whether or not this Elma lookalike demagnetizer from AliExpress is any good. So I bought one, and now let's test it. I'm going to start by magnetizing the screwdriver again. You can see it now picks up the screw, and when we put it over the sensor, you can clearly see that it's magnetized. Now I'm going to demagnetize the screwdriver, see if it picks up the screw, which you can see it picks it up and then it falls off. So it appears to be a little bit magnetized. And when we test it on the app, the screwdriver has not returned to the previous level, demonstrating that it removed some of the magnetism, but it's not strong enough to remove it all. And that's a fail in my book. All right, let's regulate this movement. All right, so we have our ST3600 on the mic stand. We are going to change our period. When I get into regulation, I like to set the period a little tighter. So we're going to go up. Let's see, we'll go take it down to 4 seconds. And here we go. So I've got the lift angle set at 46. This is what I've tested and determined that this movement lift angle is. The ETA 6497 has a lift angle of 44, so a lot of people assume that's what this is. But it's important to understand that this is not an exact copy of the 6497. So this escapement the angles in this escapement are a little different than the 6497, hence the different lift angle. You'll first notice that we've got a really nice straight trace line. I haven't done anything to this movement. This is exactly the way it was when it came out of the box, basically. So I haven't adjusted the regulator pins or anything like that. During the testing, I'm going to give it till the 6 number pops up, and that's where I'm going to grab the reading. So on our first position, we've got dial down 11, 275, and 0.6. Now we'll go dial up. Now, one of the things that's important when you're regulating a movement of this quality, right, is that you have to have realistic expectations. There's different qualities of movement, obviously. You know, you've got inexpensive movements, which I would consider this an inexpensive movement, even though it does have a lot of potential. And I've had some that were really, really good as far as accuracy go. You have to have realistic expectations. You can't expect it to perform like ETA top or chronometer style movements. Okay. Now we are going to test in 5 positions. I do dial down, dial up, crown left, crown down. I do not do crown right. And as I've talked about before, crown right is typically the weakest position in the movement. And manufacturers actually design movements so that natural faults of the escapement fall under crown right. Now, when you get into higher end movements, that's not going to be the case. So dial up, we're at 5, 287.3. Now we'll go crown up. So realistic expectations. Now, what we're trying to do is after our service, we want the watch to run as good or better than before we even did anything to it. And I'm going to put up the numbers that we had when we first did our initial readings. And you'll see that we've got a dial down position of 9, dial up at 6. The amplitude in the dial positions was 287 and 283. And then we had crown up at 1, crown left at 0, and crown down at -6. Now, not bad, but on these readings, we have a delta of 15, and that's really what we want to improve. So our crown up readings, we're at 11, 247.5. There's our crown left. Obviously, we want the stem and the crown pointing to the right because the movement is backwards. So the delta is the difference between the highest number and the lowest number. And on our initial readings, it was 15. Now, in a movement of this quality, 15's at the top end, right? Anything over that, and that's pretty much signaling there's trouble. I would like to see it closer to 10. When you get into high-end movements, that delta will go down to 5. And it's what we're really talking about here is the difference or the grouping of all the rates being very close together. Okay, the higher the delta, the farther the rates are apart, and the less it's just going to have a less timekeeping ability. It's not going to be keeping great time. Okay, so now we're at 16, 261 and 0.3. Then we'll do our last position, which is crowd down. Okay, now the delta number is really the number one number that a professional watchmaker is going to look at. You know, everybody thinks about rate, and obviously rate's important, but watchmakers care about that delta number, because that delta number gives you a much better overall picture of how well the movement's performing. All right. So if you have a low delta, you're going to have a good rate. Right. So they kind of go hand in hand. So the first thing that we're going to look at here is, let's talk about the beat error, because everybody loves beat error. Beat error is basically the tick and the tock of the movement, right? It's the oscillation or the vibration of one side of the escapement timed to the other vibration of the escapement. So the balance wheel swings one way, it swings back the next way, it comes around to the line of center, and the beat error is the difference in the time of those two vibrations. So here on our crown down position, we're at 10, 247, and 0.6. So let's look at our rates. We have 11, 5, 11, 16, and 10. Okay. We have a difference in the dial positions of 6. So our delta for dial is 6. That's not bad for a movement like this. I mean, obviously, the closer they are, the better. But 6 is certainly an acceptable number for this movement. Our delta in the vertical positions, we have 16 and 10. So we have a rate difference of 6. That delta is very good. I mean, it's exactly the same as the dial, so we can't complain about that. The delta between the dial amplitudes is 12, and that's a little higher than I would like to see. But it's, again, I'm not going to worry about it, because what I'm looking at is our overall rates are pretty close together. So it doesn't look like we're going to have much problem improving this rate. So one of the things that I look at initially is whether or not the regulator pins need to be adjusted. And like I said, these are adjusted from the factory. I haven't touched them. And here's how you can tell whether the regulator pins need adjustment. You look at the dial positions, and we have 11 and we have 5. When we look at our vertical positions, our crown up position is 11 as well. Our crown down is 10, which falls in between the 11 and the 5. So our regulator pins, this overlap between our vertical positions and the dial positions, tells me and tells us that our regulator pin is set as well as it can be. Okay? So there's no need to adjust the regulator pins. If you want to learn about adjusting Edachrome systems, again, I've done other videos on it, but for this watch, the exercise today is just to regulate this particular movement. So our regulator pins are good. We can make okay, so let's go back to the beat error for a second. The beat error in a watch that's over 1.0 milliseconds. When the beat error gets above that number, the difference in the timing on each side of the escapement on each of those vibrations, if it gets too big, that will start affecting the timing. This is a well-known fact. Okay. Some of the greatest watch adjusters ever recognized that beat errors over 1.0 milliseconds will affect the rate. If it's under that, it does not affect the rate. So you could have an average beat error of 0.9 and it really doesn't matter overall. Okay. Now, there are things that can cause beat errors that can cause bigger problems down the road. Okay. Like things like a loose impulse jewel can cause a beat error. And, that's something that would need to get addressed. But in this case, we could be pretty confident that we don't have any issues like that. So the beat error, we could adjust it down. We have a 0.6, 0.3, 0.5, 0.3, 0.6. It's really just a matter of moving the arm that holds the hairspring block, but I'm not even going to mess with it because it's close enough. Now, a lot of times people look at beat error and they really concentrate too much on it. But in this case, it's not really going to affect the timing. So now I want to look at, all we really need to do is make a small adjustment to get our all our rates a little closer. A lot of people don't realize when you're regulating a movement that if you just are looking at one position, then you're really not seeing the full picture, because if you move the regulator arm, it's going to affect all the positions, right? So what we're doing is we really want to bring these numbers together. And the way we're going to do that is by moving the regulator arm. So let's go ahead, and what I'm going to try to do is I want to bring that dial up position, which is 5. I want to bring that as close to 0 as I can without going negative. You always want to be on the positive side, whatever your average is going to be. I typically shoot for a rate of 5 seconds a day when I can. Sometimes that's not possible. This movement seems to be cooperating. I'm not going to necessarily worry about that crown left position. Even though crown left's important, I'm going to try to only lower this about 5 seconds a day so I can get that dial up position at, like I said, as close to 0 as I can without going into the negative. And all these other numbers are going to follow right behind it. So let's go ahead and make that adjustment. All right, so this is going to be a very small adjustment. And since we want to slow things down, we're going to make the hairspring or the active hairspring longer. So we're going to move our regulator pins towards the hairspring stud. And this is a very, very, very small adjustment. And what I'm doing is I found a spot to focus on the arm right here. And I'm looking at it to this little ring so I can judge how much I'm moving it. And I'm just going to make a very, very small maneuver. Tiny. I mean, maybe 1/10 of a millimeter, maybe 5/100ths of a millimeter. Very small. So now I'm going to go back to the time grapher, and I'm going to put it in that dial up position and see how that affected the rate. Well, as small as that move was, that was a 12-second adjustment. So we're going to need to take it back the other way, and the move is going to have to be even smaller than that one was. So let me go back to the microscope. Okay, so now we want to speed it up, so we're going to make the hairspring a little bit shorter. Let's try that. So it looks like we're kind of bouncing around 5 to 8. So we need to go one more adjustment backwards and see if we can kind of hit that sweet spot between 7, 8 and 0. I mean, it's very small, so that is the challenge. Okay, so again, we're trying to slow it up again. And we need to see if we can just make a micro adjustment. Let's see how that did. I could even barely see that under the microscope. Looks like we might be pretty close to where we need to be. Okay. So I think that's good enough where let's go ahead and run all the numbers again. So you can see that our rate has improved about 5 or 6 seconds per day. So you see how the dial down position has followed the adjustment from dial up, and the vertical positions should do the same thing. So we're going to let it settle in one more number. All right. So 6, 271.5. Now we'll look at our dial up position. Our last reading we had 5, so I'm really looking to get that at 0. And I would settle on a -1 as long as most of these rates showing on the screen are going to be zeros. Because for it to fluctuate a 1 degree or 1 second a day is not really a big deal. Like there's one right there that just popped up. -1. All right. So I'm going to take that -1 because we've got 0, 0, 0, 0, 0, and then -1. Amp 270. B there's 4. Now I'm going to go crown up. We were 11 seconds a day on our previous reading. Now we should see something around 6, I would think. If everything falls in line. Remember, what we're really focusing on is what that delta number is going to be. That's going to be the true test. The delta rate is the #1 indicator of the overall health of the movement. Trumps everything else. I'm going to call that 6. Now we'll go crown left. Crown left was at 16 before. So it looks like this improvement is good. I mean, if we settle in at 6 or 7, I would be more than happy. Because if that's the case, then our delta has been greatly improved. Remember, when we took our initial reading, before we took the movement apart, it was 15, our delta rate. All right, so that's 5. Take it. And crown down is going to be our last position. We were at 10 before. And this one's also looking very well. Very nice. If it stays there, I'll be very happy. 3, very, very nice improvement. So to figure out our daily rate over all 5 positions, we're going to add the positive numbers together. So we have 6, 12, 17, 20. We're going to subtract 1. That leaves us 19. Divided by 5. That gives us a daily rate of 3.8. We'll call it 4 seconds per day. And our overall delta, our lowest number is -1. Our highest is 6. So that gives us a delta of 7. If you have a watch movement with an average of 4 seconds per day and a delta of 7, that's a very well running watch. So the question is, did we improve this watch from the time it was serviced? Well, the biggest indicator is our delta of 7. That's outstanding. Our delta before we serviced the movement was 15. When we add up all our numbers, the positive numbers from our initial reading, we were at 15, 16, minus 6 is 10, divided by 5 means our previous rate was 2 seconds per day. And now we're at 4 seconds a day. So our rate went up a little bit, but our delta came down by 8 points. So now we're at 7. And that's a definite win. Now, the one thing I will point out is that our amplitude in our dial positions is about 16 degrees less than it was. Now, there could be other factors, but again, it really doesn't matter when you have a average of 4 seconds a day and a delta of 7. Can't complain about that at all. So this movement is regulated. When it comes to regulating and adjusting watch movements, we didn't even really scratch the surface today. Adjusting and regulating for good, consistent rates is really one of the main goals of watch repair, right? Nobody wants to wear a watch that can't keep time. If you want to take a deep dive into watch repair, I offer a comprehensive watch repair course from start to finish. You can check out the details at watchrepairtutorials.com. This video series is made possible by the generous contributions of my patrons. I don't make videos for views. My goal is to pull back the curtain on watch repair and make it more accessible to everyone. Patrons are able to watch all my videos commercial free, and I also upload videos exclusively for my supporters. If you like this type of content, consider supporting the channel on Patreon. In the next video, I'm going to go over servicing the mainspring barrel, the different types of grease and when to use them, as well as a ton of information on mainspring winders. There's going to be tons of useful information for everyone, no matter what your level is. And because there is so much more to learn, I'll see you in the next video.